Hello, my people. I hope we're doing well. This is video one to accompany our in-class discussion of verifying trig IDs. I'm going to go back over this front page just by way of reminder, and then we'll just jump into just a ton of examples. Now, I wanted to go ahead and remind you that despite the fact that these have an equal sign, right, they are not equations in the traditional sense. Okay? In the traditional equation, and the example that I gave is 4x minus 7 is equal to 13, the question that's sort of lurking, that's sort of implied by that equation is, for what value of x is this true? And so, your job is to find out which one is true, which is why you're asked to solve equations. In identities, the equal sign, not a question, right? It is actually a potential statement of identity, meaning that sine squared x plus cosine squared x is equal to 1 is not true for a particular value of x, but is an identity, meaning that it is true for all x. So it doesn't matter what value you plug in, as long as you plug in the same value for both x's, you will get 1, period, the end, okay? Now, that means that since the equal sign is kind of a question mark, hey, is this really equal? Asking you to verify the fact that it is indeed equal, because the equal sign is the substance of the very question, you cannot assume it, right? Just think about that logically. You can't assume what you are attempting to prove in the process of proving it. And so if you just think about it from a logical standpoint, then it makes sense, as long as you understand that it is a different type of question. Basically when you are given this question right here, this is not for what value of x are these equal. The question is, are these indeed equal for all x? Okay. So a couple of guidelines moving forward. Because they're not equations in the traditional or conventional sense, you cannot work across the equal sign. The sort of thing that you learned in Algebra 1 when solving equations, that guideline of what you do to one side you must do to the other, doesn't apply here, okay? You have to treat each side as independent expressions, not as parts of an equation. Now, because that's the case, I would highly recommend, if at all possible, and for a vast, vast majority of these problems it is possible, that you work on one side and leave the other side alone, okay? All right, let's go ahead and jump in. And in the process of doing this, I'm going to try to illuminate kind of the questions that should be going through your mind. I mean, part of what I'm trying to do over the next year is I'm trying to brainwash you, and all education, is a form of brainwashing. I'm trying to brainwash you, and what I mean by that is I want to author the internal monologue that goes on in your head when you encounter mathematical phenomena, okay? And that being the case, I will constantly be asking questions and answering them, not because I'm trying to provide some sort of rhetorical flourish for these videos, but primarily because I'm trying to get you acquainted with the style of questions you should be asking yourself, so that over time you will start asking yourself those questions, and hopefully it'll be something even creepier than that. You'll start hearing my voice in your head. How fun would that be? Okay, so we said, like we talked about in class, we need to take a look at these and we need to discern which side is more complex. And on the first one, that's kind of a toss-up, right? I mean, I have a binomial squared, or I have a binomial of the second degree on the right-hand side. Let's go ahead and work on the right-hand side. Now, I know that on the left-hand side, I'm not going to work on this side, but the form and the types of trigonometric expressions that I have on this side will dictate what I want to do over here. Now, over here, there is all tangent. All tangent. There's no secant over here. So that secant must be changed. Well, it's fantastic. We actually have a way of changing that. And the way that we change that is we use our Pythagorean, and we call it tangent squared plus 1 instead of secant squared. Now, if I then sort of move these terms around, reorder it, and I can, as long as I keep the signs the same, it's all addition, and therefore I can move it around because addition is commutative. I should notice that this is Pythagorean in its structure, right? It is of the form u squared minus 2u plus 1, where tangent x is your u, okay? So if it's of this structure, then it should factor the same way, and it does. We get tangent x minus 1 squared. Well, that's 1 minus tangent quantity squared. This is tangent x minus 1 quantity squared. But we also need to remember that any difference that is raised to an even power can be flipped around, right? Because when you flip it around, all you're doing is turning it into a negative. Well, that negative is then squared and it evaporates, right? And so in doing so, we have verified that identity. All right, let's go ahead and look down at this one. Now we notice that this side is more complex than this side. There's more factors, it's rational in structure. This is a single trigonometric function raised to a power, whereas a whole lot's going on over here. Now over here, all I have is cosines and constants. Over here I have tangent. Now tangent squared I know has a denominator of, tangent squared has a denominator of cosine squared. And it has a numerator of sine squared. What I need to ask myself is, can this numerator be changed in form and be turned into sine squared? And the answer is yes. What I need to do is I just need to go ahead and FOIL that bad boy. And then use my Pythagorean. And then use my quotient ID. And that one actually wound up being pretty straightforward. Alrighty. Okay, this third one right here, we've done one remarkably close to that, but like I said during class today, there's only a finite number of ways that they can ask these questions, and you'll start to recognize sort of common structures as you sort of move along. So let's go ahead, and what we want to do is, obviously we want to start on this side, okay? We have, not only is it two expressions that are rational in structure on the left-hand side, they both have binomial denominators. Well, it just so happens that those binomial denominators are well situated, or well conditioned, to be able to use the conjugate. Because what I would really like to do is take those binomial denominators and turn them into monomial denominators. Yay! And if I can, and the best way to do that, or at least instinctually the first thing that should occur to you as a way of doing that, is let's see if we can turn them into recognizable Pythagorean identities such that we can then substitute in a single term, a monomial, for a binomial. And what I have here is when I actually do this multiplication, 1 minus cosine squared, and over here I have 1 minus cosine x and this winds up being 1 minus cosine squared. Well, when I combine these, and if this were a negative, I'd have to be very careful about ensuring that I distribute it across this binomial in the numerator. But it's not. It's actually plus, so I don't have to worry about it. When I combine those numerators, the cosine and the negative cosine are going to cancel, and I'm going to get 1 plus 1. This denominator becomes sine squared, and of course, sine squared in the denominator can be transformed into cosecant in the numerator. And there is our verification. Alrighty. Now this next one right here, I mean, it looks messy because everything is to the second degree. You have a numerator that's a binomial, a denominator that's a binomial, but if you actually stop and look at it, it should be really, really straightforward. That numerator by Pythagorean identity becomes secant squared. That denominator by Pythagorean becomes 1. And to call this a two-step problem would probably be a stretch. And there you go. Now this one, this next problem, is one of those classic problems that pops up in just about every single pre-cal and trigonometry book out there, okay? In one form, and we've actually already seen this in other forms, and we actually saw something like this equal to, and if I separate this fraction on the right into 1 over cosine minus sine over cosine, it winds up being secant beta minus tangent beta, right? So I've actually seen something similar to this equal to that. All I'm really doing is this is just one step removed from that. So here's the thing. I want to choose which side to work on and kind of stick with it. The left side is obviously a little more complex than the right-hand side because it has the binomial in the denominator rather than in the numerator. So let's go ahead and start over there. Now it's 1 plus sine. And I see the fact that this is 1 minus sine, and so that should give me the idea what would happen if I multiplied this by 1 minus sine beta over 1 minus sine beta. Well, this denominator becomes 1 minus sine squared beta. Now, you need to fight the urge to distribute because you're hoping that this will cancel, right? And you would then just have to factor it back out again, right? So if you're going to cancel factors in the numerator and the denominator, it's best if you leave, the numerator in factored form. We need to take that denominator and transform it into cosine squared beta using our Pythagorean. This cosine beta cancels with one of the cosine betas down here, and I get 1 over sine beta over cosine beta is equal to 1 minus sine beta over cosine beta, and there is our verification. Okay, now I'm kind of trucking through these pretty quickly because I don't have you staring at me, and you've already hopefully watched the lecture video or the classroom discussion video, whatever the heck you want to call it. And so I'm just going to kind of truck through these. And if you need to pause and go back, obviously that's the beauty of it being, in the form that it is. Now, let's go ahead and we take notice the fact that this is a product over here. This over here, not a product, okay? It's a difference. Well, that makes the left side probably a little bit more complex. How am I going to turn this difference into that product? Well, let's see. I know that tangent is sine over cosine. So tangent squared is sine squared over cosine squared. Okay, well, if that's the case, then maybe, just maybe, I can actually multiply this term right here by cosine squared over cosine squared, and that way I can get a common denominator. Now if I can get a common denominator and things cancel and simplify in a nice neat way, I may be able to turn something of two terms into a single term. And what I'm going to get is exactly that. Okay, when I actually push those two together after I have a common denominator, I recognize the fact that in the numerator, I can factor out the sine squared as a greatest common factor. And once I've done that, I recognize the fact that that 1 minus cosine squared turns into another sine squared, and you need to fight the urge to actually turn that into sine to the fourth, because that right there is your tangent squared. And so this just winds up being tangent squared times sine squared, and that of course is equal to tangent squared times sine squared. And there is our verification. For some of you, the struggle is going to be to fight the urge, fight those Algebra 1 urges that say, okay, well, those two can be combined, so I should, okay? At this point in your mathematics career, you need to recognize the fact that just because you can doesn't mean you should, right? Just like up here, you can distribute this cosine across this binomial. Should you? No, you shouldn't. You should leave it in factored form so that you can do this cancellation in the next term, in the next step. And so it's that just because you can doesn't mean you should kind of logic. So let's just keep that in mind as we move forward, okay? Let's go ahead and do these next two, and then I'll kind of call it quits for this particular video, and I'll start another one. Now this should look similar in form to this. And in fact, it's the same variety of question. And what you're going to do is employ exactly the same strategy. What I need is secant squared minus 1. Well, in order to get secant squared minus 1, I'm going to have to multiply that left-hand side by the conjugate of the denominator over itself. Now, once I've done that, again, being careful not to fall into those Algebra 1 instincts of, ooh, I can distribute, so I should. No. Okay? This denominator, the whole reason why we did it is we wanted to transform it by means of the Pythagorean into tangent squared. That cancels out. That was kind of the point, right? And I get secant x plus 1 over tangent x, and that is, of course, identical to what I have on the right-hand side. Okay? Again, like I said, this should start to get a little bit repetitive. Okay? Now, let's go ahead and look at this next one. I should notice, first off, that the right-hand side is arguably a little more complex. But you should also notice the fact that they have the same structure, right? And what I mean by that is you have a difference over a sum. Now, that may be relevant. It may not be relevant. But we at least need to entertain the possibility that there's a way of multiplying through, kind of like we did in that one in the lecture, to change the left side into the right side. And after further examination, there is no such way, okay? What I need, however, is I need a way of getting sine and cosine together. Now, if you saw sine x and plus cosine x, let me put it this way. If I saw sine x plus cosine x, and then in the next step I saw something plus 2 sine x cosine x, I might think, well, gosh, that's the middle term of having squared this. Okay, and that would mean it becomes that. Well, that's actually kind of convenient, because what happens when I combine those two? I'm going to get 1. So 1 plus 2 sine x cosine x is sine x plus cosine x times sine x plus cosine x. Okay, well, let's see whether that actually helps, okay? Let's see if I can actually do that. So let's multiply, because if I do it to the numerator, if I do it to the denominator, I have to do it to the numerator. Okay. Now in the numerator, that's going to wind up being the difference of 2 squares. Okay. In the denominator, and I've already done the work, so I'm just going to go ahead and skip that step for our purposes right here. I'm going to get 1 plus 2 sine x cosine x. And you might be thinking to yourself, yeah, but that is not that. Yeah, but it's not far off, because despite the fact that you have a sine squared and you have a cosine squared, what's missing over here is cosine squared. So can I then also, okay, I want to keep the sine squared, but can I turn that cosine squared into 1 minus sine squared? Okay, because here's the thing, you don't have to be transforming the entire numerator. You can actually just do part of it. Now when I distribute that negative, it's going to be sine squared minus 1 plus sine squared x, which gives you 2 sine squared x minus 1 over 1 plus 2 sine x cosine x, which is, of course, identical to the other side. And the reason why I recognized that I could do that is over here, despite the fact that that's a 1 and that's a 1, over here each one of the trig functions was of the first degree. Over here, this is a second degree term, and because this is one trig times another trig, that's a second degree term as well. Okay, well, I have to multiply both the numerator and denominator by something to get it from first degree expressions to second degree expressions. And then, of course, something has to cancel out by Pythagorean in order for trig function terms to become constant terms, the 1 here and the 1 here. And so I had to multiply by something. And, you know, I mean, here's the thing. If you didn't actually see the fact that, if you didn't actually see 2 sine x cosine x and think to yourself, well, gosh, that's the middle term of having squared that, at the very least, you could, you know, try multiplying by both conjugates, right? Multiply by sine x minus cosine x over sine x minus cosine x. That winds up being a false start. And then you go back and you try the other one. And when you try the other one, all of a sudden, you actually find that you're on the right track, okay? But like I said during the lecture, there's more than one way to do a lot of these problems, and so don't sit there and do nothing, okay? You have a strategy sheet, you have your fundamental ID sheet. What you should be doing is just trying stuff out, okay? It should be sort of exploratory, because there's not one way to do these problems, and it really is a matter of exploration, because they are kind of logical puzzles. We'll call it quits on this particular video right now. I'll probably do one more video. I will not only be doing the problems that I had wanted to do for the next video, but I'll be doing the ones that I couldn't get to during the lecture as well. So these videos will be supplemental to the lecture in more than one way. But if you have any questions, please do email me or shoot me a message. Bye.